Excellent. I like it when the lady yells at me. So we'll start first by indicating that the entire ring has a charge of Q, and we are interested in the electric field at its center. And we're going to say that it has a radius of r, which of course gives us the indication that our lambda is going to be Q over 2 pi r.
You meant potential, right?
No.
Electric field?
Okay. No, I meant charge density.
No, earlier you said the electric field. Did you mean potential?
We are finding the electric potential.
Okay, cool.
Electric potential. Because the electric field at the center is 0. I think we can all say that without having to do any work, right? So when we're looking at the center, the electric potential is not going to be 0 at the center. The electric field is only 0 at the center because for every contribution to the electric field, say from this part of the ring, which would give us a contribution to the electric field in this way, there's another part of the ring directly on the other side, which gives us a contribution to the electric field that is in opposition. So there's lots of contributions to the electric field, but they all cancel out because the electric field is a vector quantity. The electric potential is not a vector quantity. And because of that, the electric potential at the center will not be 0, because for every contribution from this part of the ring, there will be just another contribution from this part of the ring that adds to it. So in order to calculate the electric potential from a charge distribution, we have to come up with an integral that sums the potentials together. Now, we've been pretty lax in doing the integral part. That ends now. My expectation will be that because we don't have to deal with the vector component part of this, that I can ask you to do this derivation, because the calculus might not be so terrible, but that doesn't mean it's going to be easy. So we're going to start by learning how to build the integral, and it's very similar to what we did last time. It involves us picking a piece of our geometry and using that as the start for how much this piece contributes to the electric potential. So last time we made like a little, dE, we're going to have dV, indicating how much this piece of charge contributes to the total electric potential. So to do that, I'm noticing that because this is a ring, this represents a small length. So the amount of charge there, dQ, is going to equal the charge density times the piece of length. This is an arc, so I'm thinking ds is a good sign or a good bit of integrand to use. And again, what this is this is a piece of charge equals the charge density times the piece of, I'd say length, but remember, in the general sense, your first job is to break your object up into pieces, so you could have a piece of length, a piece of area, or a piece of volume. In this instance, we're using the ring, so this is a piece of length. So that's your first step, is break your object up into pieces. Now, your second step might be harder, but that's to try and determine the best geometry to use. And I think that's not hard here. I think we're going to use something that's based on the circular nature of this geometry. And you don't have to do much with that information except tuck away how you would point to each piece of your object. For example, I might say that here's a piece right here. If I wanted to point to that piece, I would have to go out a distance r and angle 0 degrees, and maybe set this as my reference for 0 degrees. or my reference for the angle. We need some way to reference the pieces so that I can say, okay, if this is my reference point, how do I know where this piece is? Well, I would go out a distance r, but also move over an angle, say theta. So I can point at this piece. What we're trying to do is come up with a way in which we can describe where every piece of our ring is, because we're going to have to sum all of those pieces, and that's where we use our calculus. So though I say my piece is ds, what I really want to put here is information on how to point to where that piece is. So I might say that I could express ds in terms of other information. Information like, well, ds could also be described as r d theta, meaning this is d theta. It's how big my angle measure is, my sector of my circle. And I could go ahead and express the size of that piece in terms of different pointers. Now, this is just trying to find a way to express where each piece is and how I could define the size of each piece. There's lots of ways to do this. None of them are the right way. They're just different ways. For this one, it's hard to make a mistake because every single piece is the same distance away. So every single piece contributes kind of the same amount. But we're trying to look at the fact that our future won't be like that. So I'm trying to give you steps. So step one is trying to find a piece of charge. Step two, find a way to point to each piece of charge. Step three is going to be to use the definition of the electric potential for a point charge, but adjusted for a piece of charge. Good so far? So we're going to start looking at how to deal with this now. First thing I want to do is start building an integral. And I'm going to look at my definition of electric potential for a piece of charge. I've got a way of substituting in my piece of charge based on the geometry, and I'm going to decide which way I want to deal with my integral. Oops. This is one way to write it. I could also write it now. The decision we're making here is more about how we want to do our integration. Our integration is what actually sums up all the contributions. And in doing our integration, we're doing a summation. And I know that some of you are just getting to this point in calculus. So I'm going to be very, very diplomatic and very, try and be very complete. This part is determining how we're going to be taking our integral, because we're going to be integrating both sides. So when we start considering how we want to express this, that part of the geometry usually is reflected somewhere in your equation. What I mean by that is ds represents an arc length. I could decide to integrate both sides around the entire arc of my circle. Meaning I'm going around a whole circle, so I could go from 0 to 2 pi r. That adds up every piece all around my circle. The question I have to ask myself is there any relationship between the arc length and the radius that I have to be aware of when I'm doing my integral? Meaning, is any of the variables listed here related to ds? And the answer is kind of. The radius of our circle is related to the circumference of our circle, which means they're related to ds. But does the radius change as we go around the circle? No, it doesn't. So I need to be aware of how these things might be related before I just start throwing in information about my integral. Because I don't have to do it that way. There are other ways for me to express how my pieces are related. So is the angle related to the radius? Well, I don't think the angle is related to the radius at all. It might be easier for us to do this in terms of the angle, since the angle and the radius aren't related. This decision only gets better with experience. Having seen it a couple of times helps, and understanding what it is that we're doing when we take the integral helps the most. So we can actually use either one of these formulations to figure out what the total electric potential is. Neither one is better than the other, but I'm going to use this one. And I have two reasons why. First, I think it's always best if you can use something that has the least amount of assumptions to make. Using ds assumes we know ahead of time what the shape of our surface is. Now we know it's a circle, but it works less well if our arc length isn't based on a circle. Pointing to an object, though, by telling you what its theta coordinate is easy, and it's more fundamental. So I tend to like using more basic pointer variables, which is why if I can express something like a length in terms of something more like an angle, I will. I just think it's easier. So we're going to do that one. We're going to express our length as r d theta, and that way we know that to integrate over a whole circle, we have to take theta and point it at 0, and then choose every single possible theta between 0 and what? 2 pi. That's right. So that's how I decide what my limits are. I'm going to go between 0 and 2 pi. That tells me to add every single piece of my contribution to the electric potential for the entire circle. Now, you can't take the integral of one side without taking the integral of the other, but the integral of the other side just gives us potential. It's not a particularly big deal. So this is pretty small. Let's go to another page so you get a nice clean look at this. So I have the integral of dv equals the integral of lambda r d theta over 4 pi epsilon naught times little r, evaluated from 0 to 2 pi. Now, before we integrate, we have to look for whatever relationship r has with theta. When I look back, I think r is the same for every piece of charge. Every piece of charge is the same distance away. So I think it's going to be pretty easy for us to look at the relationship between r and theta. There is none. R is the same for every theta. So over here, I'm going to replace little r with big R in my integration. I've effectively looked at the relationship between the variables and my d whatever. So I should go number by number, but we know this doesn't have anything to do with d theta. We know that this is a constant for every d theta. And we know this is a constant for every d theta. Now, those things don't have to be true. You could have a situation where the charged ring is non-uniform. And so some places have more charge than others. Lambda wouldn't be constant. It could have a non-linear or non-uniform charge distribution. But we'd have to give you what that charge distribution was, a function or something. But it seems to me that all of this doesn't have anything to do with theta and doesn't change when theta changes. That's what you're really asking yourself. Do any of these change when theta changes? So they don't. So I can pull everything that's a constant out front. And of course, I can also cancel the two r's, giving me lambda over 4 pi epsilon naught times the integral of d theta from 0 to 2 pi. Now tell me, am I going too slow, or is this a good speed so you understand all the steps? Because to me, I feel like I'm going glacier slow, but I want to make sure you're catching all these pieces, because eventually you'll have to do this on your own. Okay, so what we should be left with is something that we can integrate. And what I mean by that is we should have something fairly simple. This class isn't as much about the calculus as you might think. So whatever's here, I expect you can integrate, that you have a tool set to integrate this. Now, you might not have all the tools you're going to need for the year for this, but you do have this one, because it's just the integral of 1 with respect to theta, which means that's theta to the 0 power, which means when I take the antiderivative, I get back theta to the 1 power. And I'm going to evaluate that theta from 0 to 2 pi. We've been talking about taking integrals. I feel confident that I'm allowed to do that. Except, wait, I'm allowed to use this straight line. I don't have to use the stupid bracket. Yeah, I like the straight line better. I always like the straight line better. Which is just going to be lambda over 4 pi epsilon naught 2 pi minus 0. Not particularly exciting, I know. Because when we're done, all we're going to get is lambda times 2 pi over 4 pi epsilon naught. And that's our answer. Cancel out the 2 and cancel out the pi. And we get lambda over 2 epsilon naught. Now, this is not the answer, but it's really close to the answer. The reason why I have to say it's not the answer is because we made up lambda in this problem from variables that were given to us. So sometimes, most times, when you've done your integration, you will then have to substitute back the variable you created that contains the information about lambda. So which of course, if you're at all wondering why we did this exercise just to get the exact answer that we had originally when we started. I mean, you do realize that that's what it is, right? It's Q over 4 pi epsilon naught times R. It's the exact thing for a point charge. It's because what we really did is we created the one situation where being at the center of some object is just like being that far away from the point charge. Why? Because we took a point charge and spread it out equidistance away from us all the time. So every single piece contributes the same amount. So relatively straightforward as to why this is our answer, but that's our answer. That is the electric potential at the center of a charged ring. Questions? I'm sure there's lots. Like, I don't know what you're really asking when you ask for the electric potential for a charged ring, but I just followed all the steps, and every individual step made pretty good sense to me because you explained it, Mr. Shelton. But then someday in the future, you're going to say, find the electric potential for a irregular trapezoid, and then I'm going to feel like I have no idea what to do. And I'd be with you on that one. You know, a regular trapezoid would be hard. So that's probably not on the test. But I do want you to understand that going through the process for the charged ring was supposed to point out two things. First, there's a series of steps you can take in order to take a organized charge distribution and determine the electric potential some distance away from it. Second, this should have also pointed out that the electric potential doesn't require us to look at the direction. So by summing all of the contributions to the electric potential, all we really had to understand is that our point at the center had all of Q acting from the same distance away, which is why we have all of Q acting from the same distance away. Matt? That's right. And that's, I was hoping somebody would point that out. If you have a arc length that isn't a full circle, but you're told it's charged Q, if we're still looking at a point that's at the center, you don't really have any work to do here. Because every one of those points is the same distance away from the center. And will still sum to be the same amount of electric potential. Electric potential is based on how much charge there is. And since it's spread out in such a way that it's the same distance away all the time, no big. Now, this is much different of an object than the ring node. Because this object, all of that charge is on one side. So there would be a clear electric field here too. Where in the other example, there wouldn't have been electric field. So don't assume that they're the same when it comes to how they would behave in space, but you can assume the electric potential is the same, sure. That's like, what if I gave you this? And this has been on the exam. Part of this has been on the exam already for you. If you have a ring where half of it was positive Q and half of it was negative Q, well, there'd be an electric potential of 0. And I don't have to do any work on that, but there'd be a pretty solid electric field here. Now, am I going to ask you to calculate that? Sure, you should be able to calculate both. The size of the electric field and the electric potential being 0. And you don't have to calculate the electric potential. You can see it and know that it's 0. Electric field, that would be some work. That'd probably be a lot of work. So let me pause for just a minute. Are you following this discussion okay? It makes reasonable sense that we're just trying to find a way to add up all the pieces. I want to show you something because I think you know this, but perhaps it's never been expressed to you this way. Integrals are a way of adding. So what if instead of a ring, we had a disk? And I wanted to find the electric potential from the disk, because it would have an electric potential at the center. I don't know what that electric potential would be, but if the whole thing was charged Q, the electric field would be 0 at the center, but the electric potential wouldn't be. There would be some electric potential at the center. It would take some amount of work to move a particle to that center and put it there. Yeah? Yeah. So let's make this an insulator. Is that okay? Now, the reason this isn't going to have the same electric potential as a ring is because every contribution to the electric potential isn't the same distance away. This contribution is a distance r away, and this contribution over here is a different r away. So if I wanted to sum up all of the contributions to the electric potential, that would be hard, because there's like a lot of rings here, each ring contributing a different amount. because it's a different distance away. We should still be able to do this. We should still be able to figure out what the electric potential is, even if we spread it all out on the surface. So before I do that, I want to show you something to prove something to you why this works the way it does. And to do that, we're going to ask a different question, a question that's easier. Before we have to do the whole thing about what the electric potential is, I'm just going to break my piece up and say that what is the area of this entire surface of a disk? Now, I know you know the answer. I know you understand that the answer is pi r squared. Do you know why it's pi r squared? Go ahead. Antiderivative of the circumference. I don't even know if that's true or not. That might be true. I'm glad. It's not that I don't know the answer to what that is. It's that I want to demonstrate that this is a sum, that it can be found by summing each piece of the disk. I want to break the disk up into pieces, and I want to add up all of the pieces of the disk. I know that you guys learn these things in math to show how they're related. I know that. Clearly, pi r squared and 2 pi r look very much like they are derivative and antiderivative. But there's another way to think of it. I need you to stop thinking of it as a function and to think of this as a sum. The sooner you do, the more easy it will be to break our complex shapes up. So to think of this as a sum, I'm going to take a piece of my disk. We want to find a way to point to it and describe it. So I'm going to draw my piece a little more carefully because I want my piece to be not a square, but I forget what they call this, a sector? Is that the right word to use for a circle? A piece of a circle like this? Or a segment? I can't remember what the right word is. I'm not going to sweat over it. I'm taking something that looks kind of like a square, but isn't. What I mean by that is this side and this side are the same length, but this side and this side are arc lengths. Come on, be my friend. All right, nothing's working the way I want it to, but you know, hey, it's not like I'm in my room. Should be happy about that. So let me make it bigger. Oh, there we go. Made it bigger. All right, so I want you to imagine that we could point to where this piece is. I'm drawing two pieces because this is a distance r away. So r away from the center. Each piece is going to have a width. My width is going to be radial, so I'm going to call that width a small increase in r. Also, there's going to be a length, this side. Now, this length and this length aren't exactly the same. Except in my head, I know that dr is really, really small. But if I want to find each of those lengths, this arc length right here is going to be r d theta, where this is d theta. Because an arc length is your radial part times how much angle you sweep out. Now this side is actually going to be r plus dr times d theta. I know that. And I know that that's not great. So I'm going to fudge it and say that if dr is really, really small, then this and this are probably almost the same size. And we do this kind of stuff in calculus all the time, right? dr, by definition, goes to 0, which should make r plus dr about the same size as r. Can you guys be okay with that? Because what I want to do is I want to find the area of this piece. And the area of this piece could be its length times its width. R d theta times dr. That would be its area. You guys okay with that statement? Okay. So putting that aside for a minute, if the piece of area is equal to R, you guys can see red. If the piece of area is equal to R d theta times dr, then I could find the entire area by taking the integral. I would add up every one of these little squares over the entire disk. Now, there are some problems with this. The first is I have two different little derivative pieces here, which means that my actual integral is going to have to be done twice, one in each dimension. And I'm going to have to organize it so that when I do this integral, I do them in such a way that if r and theta are related, I have to do the inside of this first and then the outside. Now, ours is never going to require this much thought. Ours is always going to be very much more straightforward in that all we will ever actually have to do is put all the stuff that has r in it with dr and all the stuff that has theta in it with d theta, like this. We can use the property where it doesn't matter what order we multiply in. So I'm just regrouping to have r times dr and then times d theta. Then we can actually separate the integral. Do the integration that has to do with d theta as if it's all by itself, and the integral that has to do with r as if it's all by itself. We do have to set our limits, and I'm looking at a disk. So I think I want r to go from the center, 0, to the edge, capital R. And I want theta to go from whatever this is, we'll call that 0, all the way around. So all the way around is so the area is going to equal whatever happens when I do this double integration. Now it is a double integration, so I do have to do two integrations here. I'm going to do the r part first. I have r integrated with respect to dr, so I have to find the antiderivative of r. That's r to the 1 power. So my antiderivative should produce r squared, and then I have to take the number ahead and divide by my new exponent, so 1/2. Any question about that? We've done this one before, right? And then I need to evaluate it from 0 to r. All right, set this aside. Let's do the next one. I'm going to go from 0 to 2 pi, the integral of d theta. We just did this, so I don't think I have to go through the whole rigmarole of telling you that there's an implicit 1 there, which is actually theta to the 0 power and all that, right? Am I good to just say the answer is theta here? Evaluated from 0 to 2 pi. Now you still have to put in you still have to put in your limits. You still have to do all of that stuff we would expect to see here. So I'm still going to have to do 1/2 r squared minus 1/2 0 squared. And then I also have to do on this side 2 pi minus 0, which is still just going to give me 1/2 r squared times 2 pi, which gives us exactly what we knew from the start, pi r squared. But we didn't just find the antiderivative of the circumference. We actually added up a piece of the area over the whole shape. And the reason why this is important is this is going to allow us now to do this for any kind of electric potential or electric field. All we have to know is what is the relationship between the charge density and the area. But it does require, a double integral. And of course, you can also imagine that if this was three-dimensional, what would that kind of produce? It'd be a volume, right? So triple integral, one for length, width, and thickness. Now I know this is probably, looks like way hard, but you do realize that all we did was broke up our object into a small piece. And then starting from there, figured out how we could define an area of that piece, and then added up all the pieces together. Because that's what I want to do right now. I want to have a disk of charge. And actually, what I'm going to ask you guys to do is tonight, I want you to consider a disk of charge that has a charge density of Q over pi r squared. I want to see if you can apply what we just talked about to a whole disk. So follow what we did for the ring, combine it with what we just did for the disk, and see if you can find what the electric potential at the center of the disk is. Just try it. Spend 5-10 minutes trying. All right, that's it for today. You guys at home, have a nice day. Be happy you get to escape. Be sad that they didn't cancel the class. See you all.